All right. Welcome to a hopefully brief video about integration by parts, which is, of course, a method for integrating functions that would be otherwise unintegrable using the current methods that are available to us as of Calculus AB. As a quick refresher to what we have available exactly, we have our basic rules like integrating a constant, which is going to be constant x, or integrating maybe a power, should just be that higher power over n plus 1. And we have the addition, subtraction rules. F plus g is just equal to integrate f plus integrate g, and so on and so forth. And then we also have our more advanced tools, specifically use substitution, in which we replace inner functions with differential variables. Differential variables, so we can abstract away all the messy inner workings of the function to use a simpler rule, like one of the ones we just listed above, to actually integrate the function. Essentially an inverse application of the chain rule. Now, all this might sound like a lot, and you can certainly solve a lot of integrals using just these concepts. Surprisingly, these are not capable of integrating all things, and that might come to a shock at first. Like, is there always going to be some rule that we can just apply? And the thing with integration is that you kind of just have to try everything until something works. So unfortunately, no matter how many integration rules you learn, you're not necessarily going to be able to integrate everything that is integrable. So the best thing you can do is expand your skill set when working with integrals. And one of the most important tools to work with when integrating is integration by parts. To show you a kind of problem that you'd be required to use integration by parts, let's have a relatively simple function actually. Integrate ln x dx. Just going to put those parentheses there. Now, it may look pretty tame at first, but let's see if we can apply any other rules to this. So, real quick, we don't have a general rule for ln x times x, so there isn't just a general rule. We're not adding anything, and we don't have a general rule for multiplying things yet. And then let's see, our final tool that we have, I guess, would be integration by use substitution. Let's see. Is one of these the derivative of the other? No, because derivative of x is 1, which is not ln x. Derivative of ln x is 1 over x, which is not x. Yada, yada, yada. So at this point, we have a function that you honestly probably encounter in a calculus class that you can't integrate, which is mildly concerning given that it literally has two terms and is completely understandable. It's just a logarithm multiplied by a linear function. So, where all else fails, we need to turn to a certain kind of formula to do our integration for us. And that formula is as follows. And this is important that you memorize this formula because it's not worth it trying to derive it every time. You just need to ingrain this in your head so you can use it as a tool, especially in AP testing when time is of the essence. So the formula goes as follows. Integrate u dv is equivalent to u v minus integrate v du. That might look like a bunch of complete jarbled mess. I mean, we have a u and then a dv, so are these different functions? And it is a complicated subject to kind of talk about when we have these differential variables and we're just mixing and matching them all over the place. And of course, we don't even have dv on the other side, so where are we spawning everything in here? And it's important to remember that we're using the fundamental rules of calculus. So, just to get a quick refresher, integrating dv, is this the same thing as v? So, if you want to have v here, this v right here is going to be equivalent to, or I guess this v is going to be equivalent to the integration of this dv. So you can start to see some openings in which we can poke some holes in some integrals using this. Now to move on a little bit, let's actually start applying this to that function we just had here. So let's try integrating ln x times x dx. Now, what do you think would be the u? Well, I guess it would just be worth, since we're multiplying two functions together, and that's literally how the integration by parts works, let's just say ln of x is u, ln x equals u, and x equals dv. Well, I guess x dx. But for our practical purposes, we're going to ignore the dx and whatnot because it's not really worth it learning exactly what all these mathematical instruments do until you get into abstract algebra and whatnot, but whatever. Anyways, so let's just plug and chug. Let's say, so we're just going to say integrate ln x dx is going to be equal to u v. So we know u is ln x. And then we need to find out what v is. But remember, using that fundamental rule of calculus, if we know what dv is, we can find what v is. So integrate dv, which is going to be x. Of course, dx in there. And then minus integrate v du. So what's v? V, again, is going to be integrate x. And then du would be over x. So times 1 over x. It's important to get your parentheses correct here. Dx. Now, that looks like a complete jarbled mess, but let's just get on with it. This reduces down to ln x times x squared over 2 minus integrate x, it's x squared over 2 over x. So that's going to be ln x squared. Sorry to put these in parentheses real quick. Over 2 minus the integral of x over 2, which would just be x squared over 4. And just to verify our answer real quick, let's try actually differentiating this. I guess I can move this pitfalls a bit lower. So we've determined that this integral right here is equal to this function right here. Let's differentiate to confirm our answer. So first of all, that's going to be ln x squared, so using product rule. If we differentiate this, that's going to be equal to 1 over x squared plus 2x ln x all over 2. And then minus 2x over 4. Okay, further simplification, that's just going to be x plus 2x ln x minus, over 2, x over 2. So then what you get there is exactly as you'd expect, ln x times x, which was indeed what we originally integrated. So you can see integration by parts does indeed work. Now, it's important to realize that integration by parts is not a end-all solution to your integration problems. In many cases, the other techniques that you've learned will actually be more useful. One example, a pitfall that I've fallen into, my first problem that I tried approaching using integration by parts was sine x, cosine x, dx. Now, of course, you could approach this using integration by parts. I guess I can show you that approach real quick. U equals sine x, dv equals cosine x. Plug that into the formula, we find out that this is equal to sine x integrate cosine x minus integrate another integral cosine x, then times dx sine x. Of course, after using the fundamental rule of calculus, find that that's equal to sine squared x minus the integral sine x, cosine x. And what we found is that instead of getting a solution, we've actually completely recreated the original problem and just slapped a sine squared x here. Now, it's important to realize that we did actually gain some information, specifically in algebraic information, which we find that 2 sine x cosine x minus sine squared x equals 0. Of course, by algebra, we can find that this integral right here is just going to be sine squared x over 2, and that's our solution. As you can see, it does get you to a solution, but you have to work around the problem and use algebra in a place that you didn't need to before. Now, it's not to say that this solution isn't viable, and sometimes you will need to solve problems in a similar fashion to this. But in this case, a much better way of solving the problem would just be by integration by u sub. In that case, you can just get u equals sine x, du equals cosine x, and we find that by u du is just going to be equal to u squared over 2, which of course is equal to sine squared x over 2. We get the original solution that we got using integration by parts much faster. So that's just a demonstration of one of the pitfalls, but to sum it all up, integration by parts, very useful, not always the tool you want to use.